Okay, so at this time, is there another yes. So another way to visualize it is, this is your time at t equals 0. At t equals 0, your wave is going to be looking like this. Okay, so now we are going to draw a line wherever there is something peculiar about our shape. So here is where we start, so we're definitely going to draw a line here. Here is where we stop, we're going to draw a line there. Okay. Here in the middle, it might not be bad to add an extra point so that we know what the shape looks like. You know, here it's a straight line. If we had some other kind of curve, you want to look at what's going to help you visualize that shape at some other time. So here, the amplitude at the half point, the amplitude was 1/2. So you project that on the x-axis and you draw the line from there. Okay, and then the characteristic diagram itself does not include that original shape, even though you've used that original shape to draw the characteristics diagram. And then the idea from there is to use it to visualize it moving. If you were to draw that in 3 dimensions, you've got your time here, you see that thing going up and down over time, so it would look something like this. And then looking at it from the top, you just see those, actually the line doesn't stay on the T. We're moving at speed C, so you'd see something like that moving away from the t-axis, and looking at it from the top, you just get those 2 lines that are parallel to each other. That makes sense? Yeah? So just plot the zeta of x, go into MATLAB, you've got your zeta of x and t is equal to that function, plot it in 3 dimensions, and then look at it from the top. And if you take just the top view, you'll just see those 2 lines in your x versus t plot. Okay.
So this was for a particular wave shape where it was.
You can pick
linear.
you can choose any shape you want. It is not one particular shape.
But this example was all for a
This
linear.
example is for one particular shape, yes. So, so what you're going to do is you start, you plot your t and your x-axis, you draw the shape of your wave at t equals 0 along your x-axis. What does your wave look like? And you use the 0 crossings, the maximum points, any peculiarity about the shape of your wave. You draw a line from there with a slope of 1/c. And then from that you'll be able to look at the shape of the wave at any time or any position.
Okay, I just get, so these side curves here, you're folding out.
Yes,
So
I'm looking at it from
okay.
the side.
I just noticed you've got a deflection.
Yep. So that's my displacement zeta as a function of time at position x0. This one is my displacement zeta as a function of position at time t0. Okay. So you can use that. And for a plane wave moving forward, it's no big deal. But we are actually going to use that. You can use that to generate the shape of a string that's fixed at both ends, for example. So whatever you had to generate using MATLAB, we can do a plot and generate that same plot, that same graph. So again, the idea is to use the characteristics diagram reconstruct the wave the waveform at any time So generally speaking, so if we want to generalize that, you'll have your function zeta of x and t is some function of x minus ct plus some function of x plus c. So f of x minus ct plus g of x plus c. That function f of x minus ct is going to be constant along the line x minus ct equals constant. Okay, and that's where those characteristic lines come from. So that line x minus ct equals constant is a characteristic line, which is a characteristic. So generally you'll draw one line at the head of the disturbance. And each of those lines is called a characteristic. So you'll draw one at the head of the disturbance, that's this one. You'll draw one at the tail of the disturbance. And you'll draw other lines whenever there is a maximum, a minimum, a zero crossing, or a jump in amplitude, or a change in amplitude for some reason. So wherever there's something characterizing that wave, you draw a line through that point.
These maximums and minimums and zeros are in reference to the deflection zeta.
To the function f. So your function f, so this is my function f here. That's my already, so my function f of x and my z. So at t equals 0, my function f of x is equal to x, or f of x minus ct equals x minus ct for x minus ct between 0 and 1. Okay, so this is what's happening at t equals 0 is really my function f, represented in the function f. So you look at what's happening at t equals 0, because your wave is not going to change shape when it propagates. So whatever shape you start with is the shape you'll have from there on. Okay, so you start with that shape at t equals 0, and you look at the zero crossing. You look at the head here. You look at the tail, and you draw those two lines. Anything happening in between, you draw lines starting at 0 parallel to those other lines. Okay.
And why do we have two functions here?
Because x minus ct at t equals 0 is equal to x. So at t equals 0, this is just x, but it starts at 0, it ends at 1. Okay. So knowing what's happening at t equals 0, we can find out what's happening at any place at any time from that graph. We have two things happening. We've got an f of x minus ct which moves forward. We also have a g of x plus ct that moves backwards. Okay, so the g of x plus ct, you'll do the same thing except that the lines are going in the opposite direction. This one is constant along the line x plus ct equals constant. So your characteristic will go backwards instead of going forwards. Same slope, well, the slope minus 1 over c for those characteristics. Okay. All right. So we're going to leave it at that for now, but we'll come back to it after we've written look at after applying the initial conditions or boundary conditions. So we're going to look at free wave solution. Which is a solution given initial conditions. So let's say, we have a wave, something has to create that wave. So let's say to create the wave, we're doing something at time t equals 0. So we give that string, that rope, a displacement, and we let it go. We could give it an initial velocity, an initial displacement, and we let that go and see it transmit along the rope. So we've got the zeta of x and 0 is some function p of x, and some zeta dot of x and 0 is some function q of x. So there's our two initial conditions that we need to use to find out our zeta of x and t equals our function f of x minus ct plus g of x plus c. So again, the little f and g's, those are that's our general solution, just like we had written for the for the string of finite dimension, we had combination of sines and cosines, and then we need to apply the boundary conditions and the initial conditions to completely define what that zeta of x and t was. Okay, so this is our general solution. Now we need to figure out what those functions f and g are, and what the functions f and g are depends on what we do to make the string move. So what do we do at time t equals 0 to make the string move? Any question on that before I move on to the definite equations? So we plug in t equals 0 in our zeta.
I have a delayed
Yes.
question. So this new function that we're coming up with here, the zeta
and Q.
function at the bottom,
This one.
that one is what we've just been solving for up until now for the
That was
motions
the
of string.
general solution we derived last week.
Right, okay.
So what that means is our wave is going to be a combination of a wave moving forward and a wave moving back. What the shape of the wave is, you know, what the shape of the wave is depends on what you do to make that wave, that string, change shape.
Okay.
Okay,
All right,
so
I'm crossing.
this piece here, that was an example of a function f. What did we need to do to it to make it move that way?
And this is different from the first homework assignment type problem.
Yes, the first homework assignment, we had a string fixed at both ends. So in that case, our solution, we chose, for convenience, we chose to write that solution as an infinite sum, okay, because it was convenient. Here, we're not doing that as an infinite sum, because it really would not be very useful. We choose to write this because our string is now infinite. It's more convenient to write it as a wave moving forward and a wave moving back.
Okay.
Okay? So when you had the fixed string, you had two initial conditions. You had an initial displacement and an initial velocity. Okay? You could plug the string, or you could hit the string, kinds of things. If you plug the string, you had an initial displacement. That's what I call capital P now. If you hit the string, you had an initial velocity, and that's now what I call Q. So we are still going to either change the shape of the string, or give it an initial displacement, or give it an initial velocity, just like we did for the string. But now, because the string is infinite, we're not going to change, we pretty much cannot change the shape over that infinite length. We're going to change the shape over a certain amount of length, and then it's going to keep moving from there. Okay. All right, so that is what's happening here. And if you were to hit it with a hammer instead of displacing it, it would behave differently. You'd have a Q instead of a P. So our P is the initial displacement. We're changing the shape and to make it move. Q is initial velocity, so we're hitting it with a hammer in a certain way to make the wave move. Okay. That makes sense now?
Thank you.
Okay, so we are going to apply these conditions into our general equation. So at t equals 0, our zeta of x and t, so zeta of x and 0, it has to be equal to what we did at t equals 0 to make that string move. And that's got to be equal to our function f of x plus our function g of x. We also want the zeta dot equals to 0. The zeta dot is our function q of x. When we take the derivative of x minus ct with respect to time, we get minus c times f prime of x minus ct. Oh, yeah, and t equals 0, so we get minus c times f prime of x. When we take the derivative of g of x plus ct with respect to time, we get plus c g prime of x. So we first take the time derivative, then plug in t equals 0. So the second one, we're going to integrate it so that we get a sum of f plus g, and then we'll have g minus f, so that when we add up, we can solve for both f and g. So we integrate, and we get minus f of x plus g of x is equal to 1 over c times the integral of q, and we'll put some variable y in there because that it's varying from plus a constant of integration. I don't want to mix this y with the x. So y is our variable of integration over the length of x. So we are going to add and subtract these two to solve for f and g. So when we add the two equations, we get 2g's. 2g of x is equal to p of x plus 1 over c times the integral of q of y dy plus k. And then when we subtract, we get 2 f of x is equal to p of x minus 1 over c times the integral of q of y dy minus some constant of integration, same constant of integration.
So, can I ask, I guess I got a little lost. Where'd the y come from?
It's just a variable of integration.
Okay.
It will, I'd rather not call it x because this is not, when we integrate it, we'll end up with limits on there. I guess I should have put my limits. It's between some point x0 and our point x, this point x here. x0 and x, x0 and x. So y is just a variable of integration. If you want to call x, we can call it x.
No, I just want to make sure I'm
Because,
following.
yeah, you're starting with a function of x at the top, right?
Yeah.
And You're just
I mean,
integrating
the
over that.
variable of integration really is,
Yeah.
disappears in the end once you're done with your calculation. So it doesn't matter what you call that variable of integration.
Is there a reason you didn't want to call it y, though?
Why I didn't want to call it x, because
I'm
I've
sorry,
got
yeah.
my x here so that we don't lose track of what's x and what's just a variable that disappears.
Okay. So, but effectively, you took the q of x at the top,
Yes,
You
and I'm
replaced all the-
integrating that.
you
I'm
replaced all the
integrating
x's with y's in that equation, and then integrated it?
that. Yeah,
Okay.
yeah. You replace this x by y, so this x by y, and you integrate it with respect to y, and the limits of integration are going to be between some value that in the end won't matter when we add up the pieces to the position x, which is this position x. So,
So can I ask another just stupid question? Sorry. So
look, no stupid. It's okay.
dots are with respect to time,
Yes.
and primes are with respect to x.
Well, prime is because this is a function of one variable. That one variable happens to be x minus ct.
Right.
So taking the derivative, the prime represents the derivative of that function
With respect to.
with respect to its one variable. Here, that one variable is x minus ct.
Okay.
So I can take that derivative with respect to x, or I can take the derivative with respect to t. If I take the derivative with respect to x, it's just the derivative f prime of the function. If I take the derivative with respect to t, it will be minus c times the derivative f prime of the function.
Okay.
Because it's a function of one variable. X and t are not separated. I'm not sure how else to say that.
I'm gonna chalk it up to math. I should have remembered.
I understand where,
So it's like,
F is a linear function of a single variable.
yes,
G is.
and that single variable happens to be a combination of two variables, but f depends on one variable, which is x minus ct. That's the f of, we called that r when we came up with those two solutions. We had an r and an s. So the f is a function of r. R just happens to be x minus ct. So we're taking the derivative of that function of one variable. And that one variable happens to be a combination of two variables.
There isn't.
Yeah, so yeah, I mean, there is just one f prime because it's a variable in one function. So now that we have found our f of x and g of x, we can replace x by x minus ct in f, and we can replace x by x plus ct in g, because it's a function of that one variable. We can put any variable in there that we want, and the variable that we want are x minus ct and x plus ct. So, so we're looking for f of x minus ct. We're replacing x by x minus ct, and I had a factor of 2 up front, so we'll have 1/2 of that p of x minus ct minus 1/c times the integral from x0 to x minus ct of q of y dy minus, okay. We do the same thing with g. We find that g of x plus ct is going to be 1/2 of p of x plus ct plus 1/c times the integral from x0 to x plus ct of q of y dy plus k. So our zeta of x and t, which is f of x minus ct plus g of x plus ct, when we add up the two, we end up with 1/2. We have p of x minus ct plus p of x plus ct plus 1/c times the integral. When the k's will drop out. When we integrate from x0 to x plus ct minus the integral from x0 to x minus ct, we end up with an integral from x minus ct to x plus ct of q of y dy. Okay, so that's our zeta of x and t dependent on our initial displacement p and initial velocity q. So in order to get the displacement, we need to integrate the velocity, and then that velocity adds up to the initial displacement. Okay, so this is our solution, and you don't have to go through that whole process anymore. You can start from here. Okay, and this is called the D'Alembert solution. To the wave equation. D'Alembert. Okay, one way to quickly visualize it, and then we'll take a break, is if q of x is equal to 0. So if there is no initial displacement, then our solution becomes zeta of x and t is equal to 1/2 of p of x minus ct plus p of x plus ct. So you start with a p of x at t equals 0. You start with a shape. You're given your string a shape. What's going to happen is half of that disturbance is going to be moving in a forward direction. Half of the disturbance will move in a backwards direction. So your original disturbance splits in half. 1/2 moves one way, the other half moves the other way.
Q of x is 0 to that velocity.
Knowing, oh yes, sorry. Sometime I'm thinking of what I'm going to say next, and I'm going to talk about the displacement next. So sorry about that. I think this is a good place to take a break.